In this video, we explore the wave nature of matter, and especially the wave nature of electrons, and examine the implications for how electrons are arranged around a nucleus, or in other words, the implications for the electronic structure of atoms. Many people are surprised when they hear that Albert Einstein won his only Nobel Prize, not for his work on the theory of relativity, but for his work in mathematically and physically describing the phenomenon of the photoelectric effect. He published this work in 1905 and was awarded the Nobel Prize in 1921. The photoelectric effect involves the emission or ejection of electrons from a metallic surface when light or electromagnetic radiation of certain frequencies is shone upon the surface of a metal. We can represent this process diagrammatically, with incoming light waves hitting the surface of a metal, causing electrons to be ejected or emitted from the surface. They can be accelerated toward a positive charged plate to create an electric current in an external circuit. Since the electric current was created by light, we call it a photoelectric current, hence the name the photoelectric effect. In this animation, we have represented the incoming light as waves. In Einstein's time, light was considered to be a wave as it conformed to the known properties of waves in being able to be reflected, diffracted, and refracted. The problem was, there was no explanation as to how waves were able to impart their energy to electrons to explain the observed phenomenon. It was especially difficult to explain why photoelectric currents were only observed above certain threshold frequencies of the incident light. Einstein's big conceptual leap was to imagine or describe the incoming light waves as tiny packets of energy, called photons. The energy of an incoming photon can be transferred to an electron to raise its energy in pretty much the same way as colliding particles can transfer energy to each other. If the energy of the photon is high enough, it will eject the electron from the atom and the photocurrent is produced. Only by describing light in particle form, which we now call photons, was Einstein able to explain the photoelectric effect. 16 years after Einstein's explanation of the photoelectric effect, the French physicist Louis de Broglie reasoned that if light waves could exhibit particle-like properties, as described by Einstein, then maybe particles, including electrons, could exhibit wave-like properties. The de Broglie relationship is mathematically represented by this equation here, where lambda equals the wavelength of the particle measured in meters, p is the momentum of the particle, and h is Planck's constant. Since momentum is equal to mass times velocity, you may also see this equation expressed like this. The de Broglie relationship can be used to calculate the wavelength of everyday objects that we would classically consider as particulate matter. For example, we can calculate the de Broglie wavelength of a cricket ball. A cricket ball has a mass of 156 grams and can be bowled at a velocity in excess of 150 kilometers per hour, or about 42 meters per second. Substituting these values into the de Broglie relationship gives us a wavelength for the cricket ball in the order of 10 to the minus 34 meters. Way too small to be detected by modern instrumentation. And this is part of the reason we do not observe the wave-like properties of everyday objects. The large mass results in wavelengths so small that properties such as the refraction or diffraction of a cricket ball cannot be observed. However, with particles of very small mass, such as electrons, the de Broglie wavelength is of the order of 0.1 to 1 nanometers, depending on the energy of the electron. And these wavelengths are able to be observed and detected by modern instrumentation. The wave-like properties of electrons were confirmed in 1927, 4 years after de Broglie first postulated the idea, when it was shown that a beam of electrons could be diffracted through a crystal lattice to show an interference pattern on a detector. These interference patterns represented definite wave-like properties of electrons. So, what are the implications of wave-particle duality for the electronic structure of atoms? The main implication is that we can never be sure of the exact location of an electron. In classical physics, particles occupy a particular location, whereas waves are dispersed throughout a region of space. In quantum physics, the electron particles have a wave-like property, and they are distributed through space and not confined to a particular location. In the Rutherford and Bohr models of atoms, we talk of electrons circling the nucleus in discrete orbits, pretty much analogous to the planets orbiting the Sun. This so-called solar system model of the atom often leads to misconceptions when it comes to physical descriptions of atoms, because in such classical descriptions of the atom, both the position and energy of an electron can be determined with high accuracy and high precision. However, in the modern quantum mechanical description of the atom, we do not talk of orbits, but rather orbitals, regions of space where there is a high probability that an electron can exist. Orbitals describe both the energy and the distribution of an electron through space, rather than the exact position of an electron. And typically, the energy of an electron is known with relatively high accuracy, but the position is not. The location of an electron around a nucleus is often shown using density probability plots, such as these, where regions of high density of dots or shading indicate a high probability of an electron being found in that region, and regions of low density representing a low probability of finding an electron in that region. In the modern day description of atomic structure, atomic orbitals are used to describe the energy of electrons around nuclei and atoms, and to describe the region of space in which an electron particle wave is likely to exist. Each orbital, for example, has a characteristic energy, a characteristic shape, and a characteristic orientation of electron distribution around the nucleus. Each of these characteristics is given a label to assist in describing the distribution of electrons around a nucleus. These labels are called quantum numbers, with the quantum number n describing the overall energy of electrons within an orbital, the quantum number L describing the shape of the distribution of electrons within a particular orbital, and the quantum number ml describing the orientation of the electron distribution around a nucleus. Finally, orbitals are said to exist in subshells and shells, which we will go through in more detail in following videos. At this stage of your chemistry studies, a lot of this information will be new, counterintuitive, and abstract, and therefore potentially confusing. In all of these descriptions of electrons and electron clouds and the electronic structure of atoms, it is worth remembering that an orbital is simply a region of space. It's a region of space where there is a high probability that an electron can exist, and a region of space that has a particular energy, shape, and orientation around the nucleus. Nevertheless, an orbital is just a region of space, and these regions of space exist at certain energy levels within shells and subshells, which all combine to make up the overall electron cloud of an atom. In the next video, we will look at the relationships between orbitals, subshells, and shells, and we will also use the quantum number labeling system to assist with our growing understanding of the electronic structure of atoms.